Okay. Just 1 second, and then we start. I have to make sure everything is connected. Okay, and then here we go. So, hello everyone. I am Maura Pintor, and I'm a postdoctoral researcher at University of Cagliari. Welcome to a new event for our machine learning security seminar series. Today we have Florian Tramèr as a guest. I want to share a few things before we start. First, the event is live streamed and recorded. So if you don't want to be recorded, you can follow from YouTube. But if you want to ask questions to Florian, you can do it on through the Zoom call, and raised hands will have top priority. Then we will look at the comments in the chat. And finally, we will check the YouTube comments as well. Also, if you want to check out all the new events we organize, you can follow us on Twitter, Eventbrite, LinkedIn, or also we have a website. Luca will send the links in the chat, hopefully. And finally, if you want to know more about machine learning security, or if you want to strengthen your general knowledge about this, we have a course in the same YouTube channel where we are handling the streaming. And let me thank all people who helped me organize these workshops, these seminars. And now I'll give the stage to Antonio, who will introduce our speaker for today.
Okay, thank you, Maura, and good afternoon to everyone. So today we are really pleased and excited to have with us Florian Tramèr. He is a visiting researcher at the Google Brain and associate professor of computer science at ETH Zurich. His research interests lie in computer security, cryptography, and machine learning security. And he is currently working on the worst case behavior of deep learning system from an adversarial perspective, in order to understand and mitigate the long threats to the safety and privacy of users. So thanks again, Florian, thanks again, Florian, for accepting our invitation. And I will say that the stage is yours. Thanks.
Yeah, thanks a lot for the introduction, and thanks for inviting me to give this talk. So as you may have noticed, I sort of changed the title of my talk at the last minute, because just as I was sort of writing the talk, I just figured that it was going to be sort of a bit more fun to call the talk this way, and hopefully you'll be excited to talk about theorems today, even though it has kind of nothing to do with adversarial machine learning, or at least I'll try to convince you that they actually do have some things in common. As you heard, I actually, until yesterday, I was a visiting researcher at Google. My current status is somewhere in between vacation and unemployed until the end of the month, when I'll be joining ETH Zurich. And the work that I'll talk about today is sort of part of what I was still doing at Stanford as a PhD student, and some of the things I was doing at Google over the past year. So, as the title of my talk suggests, what I'd like to convince you about today is that we should treat machine learning defenses like theorems. And by this, I really mean sort of formal theorems, like in something like proving that P is equal or not equal to NP. And sort of this kind of statement, this theorem statement, you can sort of equate it to a statement we might make about the machine learning defense of the form, well, here's my defense, I claim it is robust. And so if this statement is kind of akin to a theorem, then the next step, of course, is to say that, well, a proof of a theorem, basically whatever convinces you that the theorem is correct, is essentially the same thing as an evaluation of a machine learning defense. And so kind of what the sort of subtext of treating defenses like theorems is that we should be treating evaluations of defenses a bit like we treat proofs. It turns out that today this is not really what we're doing. So today, when someone comes up with a new defense and you want to go out there and refute this defense, what you do is you build an attack. So you actually just directly show that the statement is false, like this defense is not robust. You go and attack the statement. And people have been doing this for a while. My colleague at Google, Nicholas Carlini, has kind of been involved in pretty much all attempts of this form. I've worked with him on some of these. And it's kind of gotten to the point where the way you distinguish these works is by like how many defenses you break at the same time. And so you can kind of wonder like what's going to be the next stage here. When are we going to see the first paper that breaks like 100 defenses at once? Like the most I found so far is this auto attack paper that looked at 35 defenses in total. So this is kind of what we're doing right now. But it turns out this is not at all how we refute theorems. Like if someone came out and said like, oh, I have a proof here that P is not equal to NP. Well, one way you could refute this is by just showing that the theorem is false. And this would essentially mean you would have to come up with, say, an efficient algorithm for FreeSat. And then you could say, well, your theorem statement is clearly false because I just proved that P is actually equal to NP. And this is, of course, not what we do whenever someone comes up with a claim that they've proven P is not equal to NP. What we do instead is we just refute the proof. We look through the proof until somewhere buried in the middle of the proof, we find like one line where things don't make sense. And then we just say, okay, this is enough. Your whole proof is garbage. Your theorem is garbage, or at least we don't know. And this is enough. Go back to the drawing board and come back when you have a proof that's convincing. And so my claim is that essentially this is what we should be doing in machine learning as well, that we should actually just focus on refuting defense evaluations. We shouldn't really care about the statement, whether something is robust or not. All we should really care about is whether the evaluation is convincing or not. And most of the time, defense evaluations are unconvincing, and this should kind of be enough to convince ourselves that the defense is kind of, we shouldn't really care whether the defense is robust or not. If you can't sort of convincingly evaluate it and tell me that it's robust, I shouldn't actually even have to go and break it. So the question then is, what makes an evaluation convincing or not? How should we actually go about writing evaluations that are convincing? And so here again, we can go to what people do with theorems and proofs. This is actually a question that comes up a lot because people tend to very often claim to have proven famous theorems like P versus NP or something. And so people like Scott Aronson, who you might know is a famous theorist, quantum computation theorist, sort of have come up with kind of informal ways of sort of quickly judging whether a theorem or a proof that they're presented for some big mathematical breakthrough is serious or not. And Scott, a few years ago, wrote down kind of on his blog a sort of 10 informal and somewhat jokingly sort of 10 signs that a claimed mathematical breakthrough is wrong and you shouldn't even bother reading it. The 10 signs are sort of, they're not particularly important. We'll actually look at some of these, but there's some, like for instance, the first one doesn't really apply to machine learning. It's basically saying that if someone gives you a proof of like a mathematical or sort of computer science theoretical result and it's written in Word rather than in LaTeX, then you should just, you can sort of, your prior should just be, this is wrong. This person doesn't know what they're doing. No one, I don't think anyone does this in machine learning. I don't know of anyone who writes machine learning papers in Word. So maybe we don't really have this problem. So that's fine. And so today I'm not going to give you sort of exactly 10 reasons how to judge a robustness breakthrough, but I'll try to give you 4. Some of these will sort of be inspired by the ones Scott came up with for mathematics, and some of them will be sort of, again, kind of only applying to machine learning. So let's maybe start with the ones that are that only really apply to machine learning defenses. And the reason they only apply to machine learning defenses is that they're kind of so obvious that Scott didn't even bother to include them in his list. So I would say the first sign that a mathematical breakthrough is wrong would be that there is no proof to begin with. Like if someone claims to have solved a problem and doesn't give you a proof, you would reject it outright. And I mean, Scott didn't include this in his list because it's kind of completely obvious. It turns out that in machine learning, this until a few years ago, this was absolutely not obvious. And I think it's still not obvious today. So what I mean by a proof in the context of a machine learning defense is that you actually try and go to really evaluate your system. You actually try and go and attack it. And this is what we call an adaptive attack evaluation. It's like you actually try and go and show that the thing really works. And this is still sort of the first thing I do when I read a paper that claims to have a defense is I just do Control F adaptive. If I don't find the word adaptive anywhere in the paper, it's kind of like, I'd like to be able to reject the paper outright. Usually this happens when I'm actually reviewing a paper. And so I kind of have to go and do a bit more work. But to me, this should be enough, like game over, you know. And even though papers have gotten better at this, like usually now when you read a defense paper, there will be some kind of adaptive evaluation. But it's going to be buried like sort of in half a paragraph at the end of the paper, right before the conclusion, after sort of 2 pages of non-adaptive evaluations, which in the context of a theorem, I would sort of say this is a bit the same as like having 2 pages of sort of sanity checks that the theorem is probably not completely wrong, and then having a little paragraph at the end, which is like, here's the actual proof, believe me, guys. And of course, no one does this. You would expect the opposite, right? You would expect like maybe a short piece somewhere that says, okay, let's get this out of the way. Our thing isn't completely wrong. And let's now spend the bulk of the paper actually convincing you, the reader, that what we're doing is correct, that we have a proof, we have a strong evaluation. It turns out that the paper where I draw this picture from actually does this very well. This is one paper from Nicholas Carlini and David Wagner and someone else whose name I unfortunately forgot, where I would say there the space taken by both of these sections is kind of appropriate, in that the adaptive section, the one that's really kind of proving to you or trying to prove to you that something good is going on, is like 6 times longer than the non-adaptive kind of sanity checks before it. So this is really kind of the first thing you should do in an evaluation, is actually try to prove that your thing works. And by this, I mean do an adaptive attack. It goes a little bit beyond this. Like imagine you read a theory paper that says something like this: here's my theorem and here's my proof. And well, the proof will be released upon paper acceptance. Like again, you would reject this paper outright. It turns out that this is also something people do kind of routinely in machine learning by basically just saying, we're not going to give you the code until later. We're not going to give you any pre-trained models, which is basically means no one can actually reproduce your proof, or at least it's very, very hard to reproduce it. And this is, again, I think something that should just become standard, is if you want to claim that you have a defense that's robust, you should have a written down sort of proof, which is essentially your best evaluation attempt at really breaking the thing and coming up short. And then you should just release as much information as possible to help others reproduce this claim on their own. So that's kind of point number 1, is make sure you actually try and prove that your thing works. Another thing that was kind of maybe too obvious for Scott's list, because it never appears, I've never seen a theory paper that does this, is it's kind of a weird sign when you have like multiple proofs for one theorem. So imagine you're reading some theory paper and it's like, oh, I've proven like P equals N is not equal to NP. And now I'm going to give you like 7 different kind of proof sketches. Again, this sounds completely bogus, but this is again what people actually do with these adaptive attacks. Like nowadays, people have sort of discovered, oh, I really should have adaptive attacks in my evaluation, because like a bunch of people have now convinced me that this is the right thing to do. So what I'm going to do is I'm not going to have just one adaptive evaluation. I'm going to have like 7 of them. And really, a strong evaluation is not about quantity, it's about quality. Like if there's one attack in there that really goes after the main principles underlying your defense, that's much, much better to me than having kind of 7 different semi-attempts at attacks, that each of which sort of tries to do just one small thing that might work and then kind of doesn't, and then you switch to something else. Overall, this just very rarely ends up as a sort of convincing evaluation. I'm not saying you should only ever evaluate against one single adaptive attack. Very often you have defenses with sort of a bunch of moving parts where there's maybe 2, maybe 3 strategies that seem obvious to try. Usually when you're going to write an evaluation that looks at like 7 different attacks, most likely like half of these attacks are obviously not going to work. So maybe just don't include them and focus on really trying to break your thing. So these were kind of the obvious things, like really try to evaluate your defense, like try to actually prove that it works, and sort of do your best effort, sort of focusing your efforts on like the attack or maybe the 1 or 2 attack types that have really the highest chance of succeeding, that really go after what is supposed to make your defense work. So yeah, so these were kind of things that people in the theory world don't even have to care about, because it's kind of established that if you want to prove a theorem, you're going to actually include a proof of it. So let's look at something that people actually do when trying to judge whether a proof is correct. And this is something that we'll see can actually be very, very useful for machine learning defenses as well. So this is Scott's 3rd point as a sign that a mathematical breakthrough is wrong, is if the approach yields something that seems much stronger and possibly even false. Let me give you an example, which is actually the example that Scott uses. No need to really understand the details here. They're kind of not particularly important. But say someone wanted their theorem is essentially that 3sat is not in P. This is equivalent to proving that P is not equal to NP. And they provide a proof of this fact. It turns out that very often when people try to do this, you can take the exact same proof and try to apply it to a very similar statement, which is that 2sat is a polynomial time problem. And 3sat and 2sat are nearly the same problem. Actually, the only way they're different is that in one case, you sort of have these logical clauses that include 3 variables per clause, and in the other case, you have only 2 variables per clause. And this very small difference makes a huge difference, because actually the 2sat problem, we know we can solve it in polynomial time. This is an easy problem. Whereas the 3sat problem, we're pretty certain you can't, that this is a very hard problem. And so what often happens is that someone will write a proof and sort of claim that with this proof, they can show that 3sat cannot be solved in polynomial time. But it seems like the exact same ideas, you could just apply them to the 2sat case, and you would also end up showing that 2sat doesn't have a polynomial time algorithm, which we know to be false. Like there exists a polynomial time algorithm for 2sat. And so this is essentially what this claim here, this sign from Scott means, is if you have a proof that seems to work even when the theorem is clearly false, then there's clearly something wrong going on. And like you should not trust this proof, because it's clearly doing something wrong somewhere. You might not have figured out exactly where, but like this proof cannot be convincing. And so my point is that you can do the exact same thing with an evaluation of a machine learning defense. If you have an evaluation that you claim sort of is a proof that your new defense is robust, and you can apply the exact same evaluation to a model that is not robust, you know it's not robust, and the evaluation sort of still passes. What I mean by this is sort of all the attacks fail, then you know something is wrong. Like this evaluation can't be good if it cannot even break a defense that we know to be broken. And so this is essentially what my co-authors, Roland Zimmerman, who was an intern at Google, and his advisor, Wieland Brendel in Tübingen, and Nicholas Carlini, and I, this is sort of the idea of a recent paper we wrote, where we essentially want to test whether an evaluation manages to break a defense that we know to be non-robust. The main difficulty here is essentially building such a non-robust defense in a way that is kind of as similar as possible to the originally evaluated defense, so that we can sort of be confident that the two defenses that we're evaluating here are sort of as similar as possible. And so we're not somehow just creating some weird defense that happens to sort of circumvent a specific evaluation. So the details are not particularly important. Just at a high level, what we do is we take a defense that someone claims to be robust, and then we chop off the last layer of this model, and we leave everything else unchanged. And what we then do is we just retrain this last layer so that we have a guarantee that at least one adversarial example will exist. So what that means is we take some clean point, we sample some point somewhere in like the epsilon ball around this point where the model is supposed to be robust, and we mislabel this point. And then we sort of retrain the last layer of the model to kind of make sure that there will indeed be a decision boundary between these 2 points. And so now we have a guarantee that for this particular clean point, there exists an adversarial example within some predetermined distance epsilon. What's nice here is that because we only really changed the last layer of the model, everything else is the same. And so if your model was somehow doing gradient masking or something weird, this is still preserved. If your model was randomized in some way, this is still preserved. And so really, if your evaluation was supposed to work on your original model, there's really very little reason to believe that it wouldn't work against this new model where we've just changed the last classification layer. And so this is what we test. We take the original evaluation of the defense, which the authors kind of said, this is our proof that the defense works. And then we see if this evaluation would manage to show that the non-robust defense is non-robust. So we really want to see if this evaluation is kind of strong enough to find adversarial examples when they exist. And we turn this into a test, which we call the binarization test. So we're essentially going to run the evaluation on this non-robust model and sort of compute some kind of score from this. The exact way we compute the score is not particularly important. You just end up with a score somewhere between 0 and 1, where 1 means your attack is very strong, and 0 means your attack is not strong at all. It cannot find adversarial examples, even when they exist. We then took 13 defenses from the past few years, which have all been broken after the fact. So for these 13 defenses, we know that the original evaluation overestimated robustness, and that some future reevaluation did a much better job. And then we sort of try this binarization test for both of these evaluations, the original one and the new adaptive one. And what we find is that in nearly all cases, the original evaluation just fails the test. So these were kind of weak evaluations that weren't capable of breaking the defense. And it turns out they can't even break a defense when we know that an adversarial example must exist. So here, if your attack was strong, it should succeed 100% of the time, and yet it often doesn't. And so we kind of know that these evaluations are weak. In contrast, the re-evaluations, which often use a much stronger attack, these nearly always pass the test. And so these are kind of strong attacks. They really work at finding adversarial examples when they exist. There are some failure cases. Like we found that in some cases, we had re-evaluations of the defenses that actually managed to break the defense. So sort of they brought the model's accuracy on the original test set down to 0, but they didn't completely pass our test. So what this means is that these attacks, even though they manage to break the defense, they're still not particularly strong attacks, in that it's still sort of possible to get into situations where adversarial examples are known to exist, but the defense fails. And this is not too surprising, in that these attacks here, I think all of them are from a previous paper that Nicholas Wieland and I wrote with Alexander Madry, where we just went out and broke a bunch of defenses using adaptive attacks. And our aim there was not to build the strongest possible attack against each of these defenses. Our aim was to break the defense. And so what that meant is we sort of tried a few things until we broke the defense, and then we stopped. And so it's not too surprising in the end that maybe some of these evaluations were still not particularly optimal. And so if you really wanted a strong attack that always finds adversarial examples when they exist, you might have to do sort of more work than what we did there. A little bit more worrisome is that our test did have some false positives. So this means these are evaluations that weren't good, that weren't optimal, but where somehow when we changed the last layer of the model and sort of explicitly introduced adversarial examples, these evaluations were always able to find an adversarial example. And so kind of according to our test, these evaluations looked good. It turns out that these evaluations here were, I would say, not completely wrong in that they did overestimate the defense's robustness, but not by a huge amount. Like the reevaluation essentially brought the accuracy down by maybe 20% or something like this. So here we have attacks that are not perfect, but they were also not completely wrong. And so in a way, I think this is maybe okay in terms of a false positive for the test. What's really nice is that those evaluations that were clearly wrong all failed the test. And so in some sense, if we had used a test like this early on, if the authors of these defense evaluations had used a test like ours, they could have immediately seen like, oh, these attacks that we're trying are clearly not strong enough. They can't even work when we know that adversarial examples exist. And so this is essentially the sign here. This is sort of a rephrasing of Scott's point for mathematical breakthroughs. Here, I would say a clear sign that your robustness breakthrough is wrong is if the evaluation that you're using fails to break even a non-robust defense. Or rephrasing this, I would say an evaluation is convincing only if it can distinguish robust defenses from broken ones. If your evaluation, if your attacks are not strong enough to do this, then you cannot hope to convince me that your defense is robust, because we could just as well be in a world where your defense was completely non-robust and your evaluation wouldn't have been able to tell the difference. And so I hope that sort of tests of this kind will become a more sort of standard thing for people to do when writing machine learning defense evaluations, and that people will also come up with maybe different tests than the specific one that Roland came up with and worked on. This is kind of a first attempt at doing something like this. It's kind of a unit test for attacks or for attack evaluations. Okay, so this was point number 3. Point number 4, this is something that is very, very cool. This is one of my sort of favorite mind-blowing facts about computational complexity. So this is what Scott says here is that a mathematical breakthrough is wrong if it conflicts with a known impossibility result. It turns out that this does exist for problems like P versus NP. People have been trying to solve this problem for like 50, 60 years. No one's come close. But somehow, over the years, we've built a very, very good and elaborate toolkit of essentially results of the form, you cannot solve this problem using X. And so people over the years have kind of shown that there's certain proof strategies that people might try to use to prove something like P versus NP that provably won't work. So it's kind of amazing to me that we have this sort of problem that everyone kind of agrees is just way too hard to solve with current techniques. We sort of have no idea how to solve it, but we can essentially prove that certain approaches won't work. This is kind of neat, and this essentially means that if anyone ever claims to have a proof, they better explain to you what they're doing differently than these approaches, that they're not using these things. And it also means that if you're trying to come up with a proof, you already know that there's all these lists of things you better not try because someone proved at some point that they're not going to work. So you're just wasting your time. So this is all sort of very formal, and you can maybe sort of imagine how you might do this for something like computational complexity or whatever. The question is, like, could we come up with something like this for adversarial machine learning? Like, could we prove some kind of theorem that would say, don't try and use some certain technique X to build robust models, it's not going to work. And so this is a question I was quite fascinated about with some point last year. And it seems like a very, very hard thing to do. So here I'm going to talk about one attempt, this is sort of one result I've worked on along these lines, which is essentially a theorem that says informally something like, you won't be able to build robust models by detecting attacks. So the setup here is essentially what some people have been trying to do, because it seems like a very natural thing to do, is instead of building a model that's kind of robust to adversarial examples, that can classify any perturbed example you get correctly, why don't we just try to detect if an example is perturbed? And if so, we just reject it outright. We don't try to classify it. We just tell the classifier to abstain. And there's many sort of security sensitive settings where this might be enough. If you know you're under attack, just abort, don't even try to classify things. And sort of intuitively, it seems like this problem should be much easier. That sort of if you give your model this extra option of just abstaining, we should probably be able to do a much better job. And it turns out that no, you in a very real sense, you cannot. And so the result that I'll present here is essentially a reduction from a detector that is robust to adversarial examples to a classifier that is robust to adversarial examples. What this means is that you basically can, if I give you a robust detector, using this robust detector as a sort of black box, you can build a classifier that is going to be as robust as the detector was. And so in some sense, the building either a classifier or a detector that is robust are exactly equally hard, because you can sort of use one to build the other. Now, it turns out that the result I managed to show is actually a little weaker than this, in that the reduction between these two problems is only sort of partial in two ways. One is that the reduction doesn't preserve the computational efficiency. So what that means is, if I give you a robust detector that's efficient, what I mean by this is its inference is polynomial time, like you can sort of evaluate the thing in practice. The robust classifier that I can build from it is going to be inefficient. It's basically not going to run in polynomial time in the worst case. And so this is kind of one way in which the reduction is not quite perfect. The other loss in the reduction is essentially we're going to halve the bound to which we're robust. So what this means is that if you have a detector that has, say, 80% robust accuracy for perturbations of some size epsilon, then the classifier that you can build from this will have at least the same robust accuracy of 80%, but for perturbations of half the size, epsilon over 2. So these are kind of the sort of restrictions on this reduction, but my claim is that even though we have these restrictions, such a reduction is still very, very interesting, because it gives us a way to sort of judge whether claims about a new defense that uses a detector seem kind of appropriate or not. So more precisely, what you can essentially get from this result is that if anyone claims to have a very strong, robust detector, they're sort of implicitly also claiming a breakthrough in building robust classifiers. So to illustrate what I mean by this, we're going to consider a specific problem, which is that of building a robust classifier on ImageNet. And we're going to consider two worlds. The first world is our world. Here, you get to use the ImageNet training set to train a model, and your training procedure and your inference procedure have to be efficient, because, I mean, this is our world. Things have to run in polynomial time or we can't run them. And it turns out that, I mean, people have been trying to do this now for a few years, and we just can't seem to get very high robustness yet using our current techniques. Like the sort of best robust accuracy we get on ImageNet is like way below the clean accuracy. Now we're going to switch to a second world, world 2, which is an imaginary world, which is exactly the same as our world, except for a very small change, is that here the model's inference procedure, and only its inference procedure, will be allowed to run in essentially exponential time. And everything else is unchanged. You can't use more training data. The training still has to be efficient. You're not allowed to use a bigger model. So all of this is kind of preserved. But you get to sort of use as much computation as you want for inference only. And now the question is essentially, if instead of world 1, we were in world 2, should we somehow expect that we would be building much, much more robust classifiers on ImageNet? We don't know the answer to this question. I mean, no one's kind of tried to build an inefficient, robust classifier, but there's sort of, we have some reasons to believe that the answer is no. And in some sense, I mean, we just don't know how to do this. And it turns out that if someone claims to have built a robust detector, they are actually claiming to have answered this question positively. They are actually claiming, I have found a way to build a very robust, albeit inefficient, robust classifier as well. And it turns out that essentially many, many detector defenses in the literature are implicitly claiming to have made such a breakthrough. So here, what I'm showing on this graph is, in blue, is the best known results for robust classification on CIFAR-10. And these results have all been like vetted independently. People have tried like a whole bunch of attacks. This is with sort of vanilla adversarial training, for which we have like very, very good benchmarks at this point, like robust bench. And so I think we have very good confidence at this point that this is currently the best we know how to do for robust classification. In red here are the claimed robust accuracies by 3 different detector defenses from the past few years. In the paper, I look at like 13 of these, but here just for illustration, there's 3 of them. And so these defenses, they merely try to detect attacks. And so they claim to just achieve much, much better robustness than what we know is possible with classifiers. But by our reduction, we know that each of these detectors actually implies a robust classifier as well, for half the perturbation size. So given this detector, if it were actually as robust as claimed, we could just go and build a robust but inefficient classifier that will be way more robust than the state of the art. And so there's kind of 2 views you can have on this. One is that, well, these papers are claiming a huge implicit improvement in robust classification. So the optimistic take is just, well, wow, this is a huge breakthrough. Congrats. But we should be somewhat skeptical of this due to how hard we believe this is to achieve. Like, people have been trying really, really hard to build more robust classifiers and so far have failed. And so for me, at least, the more realistic interpretation, unfortunately, is the pessimistic one, is that these robustness claims from these detector defenses are wrong. And in fact, it turns out that for many of the defenses, detector defenses that I look at in the paper, they are broken. So in particular, this rightmost detector defense here, which sort of claims the biggest breakthrough in robustness for classifiers, we showed in our previous paper that this detector is actually completely non-robust. It achieves 0% robust accuracy. For the other 2 that I'm showing here, I don't know for sure. I don't think either of these has been independently reevaluated. But the reduction here already serves as kind of a warning sign that these claims are very, very likely overestimated as well. And if not, well, then we have a huge breakthrough, and I think the authors should actually claim this in their paper. Like if you're going to sort of implicitly claim to have made a huge breakthrough, you should just make such a claim explicitly, and then people can be sort of appropriately skeptical about your results. And so the summary of all this is that we essentially have very good reason now to believe that robust detection of adversarial examples is essentially as hard as classifying them. And so the sort of takeaway I would have from this is kind of the fourth sign and the last one we're talking about here. The way I would phrase this in a bit more general sense is that I think you should be very skeptical of papers that claim breakthroughs using quote unquote weak techniques. What I mean by a weak technique is essentially just some technique that we know doesn't work on its own. So there's things like detectors that we kind of have even a proof that they very likely don't help. And then there's things that sort of empirically over the years we found just don't help. So things like denoising the image or pre-processing it with some like JPEG or something, or adding randomness at different places in your defense. Like all of these things people have tried a bunch of times and they never worked. And so if someone sort of tomorrow comes up with a new defense and claims, oh, this thing is way more robust than everything we've tried out before, and you look at what techniques they used, and they say, well, first we do JPEG compression, then we add a bunch of randomness, and in the end we add a detector on top, you should be extremely skeptical. This is like, these techniques are too weak to get robustness. And it's very, very unlikely that just by sort of combining them in new ways, this is going to be enough. Probably if you really wanted to get a breakthrough in robustness, you'll need a new idea or something fundamentally different than what we've tried so far. So with this, I'll conclude. This is kind of the message I wanted to convey today, is that we should treat machine learning defenses like theorems. And what this essentially means is that we should put most of our focus on defense evaluations and making sure that defense evaluations are convincing, because if they're not, then it's a bit like if I gave you a theorem without a proof, or at least with a proof that's not convincing. And it turns out we have a name for these. We don't call them theorems, we call them conjectures. And so maybe the same way, if we have a defense with an unconvincing evaluation, we shouldn't call this a robust defense. We should call it like, I don't know, a conjectured defense or something. And what we've discussed today are kind of 4 telltale signs that someone's claimed robustness breakthrough is very, very likely to be wrong. First is that there's just no proof, like you didn't try to attack your thing, there's no adaptive attack, you didn't give any code, you're not actually giving people a convincing proof, replicable proof that your defense is robust. Same thing is if you're just going to give me like multiple kind of partial little proofs, multiple partial little attacks, instead of kind of 1 or 2 really well thought out arguments that your defense works. The third thing we looked at is that your evaluation really should be strong enough to kind of be able to distinguish between robust defenses and very, very similar non-robust defenses. And we looked at one sort of test, this binarization test, that lets you do this, lets you sort of minimally alter a model into one where we know that adversarial examples must exist, and then you can check if your evaluation does the right thing in this case. And if it doesn't, then you know that your attack is not good enough. And then finally, we should be wary of papers or defenses that sort of get extremely good results using only techniques that never really worked in the past, or techniques where we sort of have even kind of formal barriers to how well they might work, like detectors. Yeah, so that's it for me, for what I want to present you today. I hope this sort of slightly weird statement I made at the beginning in the title of my talk now makes a little bit more sense. And yeah, I'm happy to take any questions.
Okay, thank you, Florian, again. This was a really inspiring talk. So I would invite the participant to raise your hands in order to put your request in the queue, and we will serve you in a FIFO order. So I see that there was someone in the chat that was writing about his opinion on the difference between machine learning and evaluation with respect to the mathematics evaluation. I don't know if Zach Nullerov, you want to say something about it?
Hi, thanks. Thanks for the nice presentation. Yeah, I just wanted to know your opinion regarding this. So as I have written, I think that right now the ML evaluations of the robustness defenses is more like trying to find a counterexample to some hypothesis in mathematics. And then we claim that, okay, if we cannot find the counterexample, then we kind of accept this theorem. But usually in mathematics, proofs are constructed in a way that regardless of the searching abilities of the counterexamples, yeah, the statement should be always true. So I think, yeah, this parallel is more about certifiable defenses where there is no, yeah.
Yeah, I think there's two. Yeah, I get your point. I think there's two things here. In a way, yes, a proof of a theorem that's correct is in a way like a certified defense. But maybe the analogy here would be something like a proof that has been like formally verified by like some logic system or something. I think the way to interpret this is more like if someone gives you a proof of a theorem, you still sort of have to convince yourself that this proof is correct, and you can never know for sure if the proof is correct. You can sort of only just read the argument and sort of in your mind kind of make up a decision like, am I convinced by this proof or not? And so that's essentially what I'm saying we should do for machine learning evaluations as well, is like maybe we can't come up with counterexamples. Maybe your defense is so weird and complicated that no one's actually even tried to attack it. But if the way you evaluated the thing is just not convincing, then we should just not consider this thing to be robust either. The same way, if we have some theorem and no one can find a counterexample to it, we still don't consider that theorem to be true as long as you haven't written a convincing proof. And so I agree that like the comparison is a little bit leaky, and that proofs are sort of much stronger objects in a sense than empirical evaluations. But the point I want to make here really is that in some sense, always trying to find explicit counterexamples for a defense is maybe just a waste of work. You know, if someone has like some bogus defense that comes out, and if you read the evaluation, you can see a whole bunch of flaws in it, and you're just not convinced that they did a good job, we should just consider this thing to be not robust until someone actually comes up with a convincing evaluation.
Yep, totally agree with you. Thanks.
Okay, so we have time for other questions. We have a question from Catherine.
Yep. Hey, thank you. It was a very nice presentation. So I have actually two questions which are somehow related. So the first one is, do you have, or did you by any chance did some sort of statistics about like how many defenses fall in which group? And then sort of related to that, would you say that like defenses that fulfill all of this, is this, for example, what is on robust bench, or like are there other examples, or like is there sort of a list of like sort of real proven defenses? Let me call it like this.
Yeah, that's a very good question. It's difficult in that, at least when it comes to adversarial examples, there's very, very few defenses that or evaluations that I find convincing, and they're kind of the usual suspects, you know, like sort of adversarial training and all its variants. People have evaluated to death, and there we're very convinced that the thing sort of works. And I don't think there's any other empirical strategy that sort of has reached that that level yet. I don't think that a benchmark like robust bench or sort of the auto attack that's behind it is enough on its own to really be convincing. I think when it comes to models that are essentially just, or defenses that are essentially just variants of adversarial training, it's a very good benchmark because we kind of know by now that these defenses don't really do anything weird, and kind of plain gradient descent works extremely well and is kind of the best we can do. Any other defense is usually doing something weird with randomness, with detectors and so on, where auto attack doesn't necessarily work as well. And so, yeah, I've actually seen now a few papers I've read where they say, oh, we do an adaptive evaluation, and like the first adaptive evaluation is, oh, we run auto attack, which is like, this is bogus. This attack was like created 2-3 years ago. This isn't adaptive in any way. It's like the most static attack ever. It just happens to be an attack that tries a whole bunch of different parameters or something, but it doesn't adapt in any way to the defense. And so I think any new defense idea that isn't sort of yet another iteration on top of adversarial training, you really have to go and do the work of thinking what is the assumption behind my defense working? How do I build an attack that really tries to challenge this assumption? And I think this actually gets even worse when you go outside of adversarial robustness, when you go into things like poisoning attacks, backdooring attacks, Trojan attacks, watermarking attacks, all these things. I would say the evaluation standards are unfortunately still fairly poor, and it's very, very hard to find defenses that's really go out and try to attack the thing in the most convincing way possible.
Okay. So we have time for another question. The next one is Tim.
Yeah, hello, can you hear me?
Yes.
Okay, perfect. So I was wondering whether we actually really do need a convincing proof. And let me explain where I'm coming from. So as in the first question was pointed out, there's like mathematical proofs which are irrefutable, right? And then you have like the more empirical evaluation based on a possible attacker model or threat model, in which you can find adversarial examples in this case, or attacks in more general, which is not this mathematical proof, but we say, hey, within this threat model, probably you can't do any better with what we do now. So as most of your work is, I think, talking about LP norm robustness kind of things with robust bench, which picks in on that. This is still very far from a real attack that could happen within a real threat model where you're looking for an adversarial perturbation. So again, do we need a convincing proof, or is it sufficient to make it hard enough for the attacker to reliably find an adversarial perturbation all the time?
How do you convince me that this is happening? I think maybe this also comes back to the first question. I think one thing that I should maybe clarify here is that in some sense all these techniques that I was talking about, that sort of Scott came up with for figuring out whether a proof is correct or not. The question here isn't really about making sure that proofs are kind of irrefutably correct or something. The point is to save yourself the effort of sieving through the like 200 bogus proofs of P versus NP that come out every year. And like basically CS theorists have for a few years now just decided we're not going to read those proofs anymore because they're all bogus anyways. And when they do, they use something like this checklist to like very quickly just say, okay, this is bogus because of this. And this is kind of what I'm saying we should be doing with defenses, that like if you can't sort of convince me that the thing is correct, just who cares? We don't care about your defense. And that we should just have a very, very high standard, essentially, for even going and really trying to evaluate a defense actively and with serious effort, because there's like hundreds of these defenses that are proposed every year, and the default should just be that everyone agrees they're not robust, unless or until someone can really come up with a very, very strong evaluation procedure that convinces people that, okay, this is maybe something we should take a second look at. And of course, then after that, there's still the whole question of like, yes, the fact that you've managed to convince me that you can defend against LP adversaries doesn't mean anything in practice. But I think that that's kind of a separate question. If you want to create a defense that works against sort of a more interesting threat model, you still kind of have the exact same burden of proof, in a way, of sort of convincing someone that this defense actually works.
Yeah, I think I agree with that, and that specifically, but I think I was trying to turn it around, and that is like, could it be sufficient to make it hard enough to find an adversarial perturbation, especially as soon as we go to more real-world constraints? It becomes already way harder to find one. So for example, if I want to attack a biometric authentication system for faces, for example, you have the attacks with the glosses. But in the end, we see that if you want to actually realize them in the real world and have them robust for all lightning conditions and applicable to multiple faces, it becomes just infeasible to still find the glosses.
Yeah. So I think if you can essentially come up with an attack model or threat model that places certain restrictions on the adversary that might be very natural, sort of, yeah, the adversary only gets to do so much work or something like this. And you can then convince me through your evaluation that within these constraints, your defense is robust. That's perfectly fine. I think, the things I talked about today were kind of about absolute robustness, but they don't have to be. I think the same arguments hold for sort of computationally hard, robust models, or models that are robust in some threat model. But I think in there, convincing people is kind of even harder, because we don't really have good evaluation standards.
Yeah, that's definitely the case. I completely agree with you. Thank you.
Okay, thank you, team. We have still time for questions. Next one is Fatih.
Yeah, hi, can you hear me?
Hi, yes.
Yeah, thanks, Florian. It was a very nice talk.
Thank you.
So I have actually two questions. I will try to summarize. The first one is, you basically, I also, your take in general, also Carlini's take is basically attacking, basically killing all the possible defenses and finding, okay, this is not working, But I'm also curious, what is your take in general? If we were to kind of develop a defense, we know that we will not have universal defenses for the attacks. So, there is this idea of using attacks actually to build defenses, right? So, as you said, that's what you did probably, right? With the if you can detect, then you can actually come up with a robust classifier. But what is your take coming from the other side, instead of just building defenses and evaluations? What is the right way to build a defense? And my second question, I will just squeeze in that one as well. The evaluations are not maybe good enough, they are not well enough. But what is the relation with the assumptions? Maybe the assumptions that they make in the evaluation, but also in building the defense, are not maybe made clear, maybe not explicit. Maybe you see you did this, the classification layer change. Maybe if they specify these assumptions that we assume they are not changed, etc., maybe the evaluations will be more valid. And what is the relationship between the assumptions being more clear, more specific, and the validity of the evaluations?
Yeah, so I guess regarding your first question, I would probably say something similar to the previous question about sort of realistic threat models. Is that, yeah, I think if you want to build a new defense, my suggestion would not be to try to build a defense that is white box robust. One, because it just seems super hard to do. was like very little progress, or just sort of incremental progress on sort of making adversarial training better and better. And it's not clear that this is ever going to be really useful in practice, where threat models are very different. But yeah, I think this is just, it's really not easy to do, because you do have to come up with sort of restrictions on the adversary that are realistic, and also that you can somehow formalize in a reasonable way as assumptions for your defense. Because then, yeah, if you want to claim that your defense sort of only works against sort of some restricted class of adversaries, you still have to figure out a way to essentially evaluate against the strongest possible adversary from that class. And that's often the part that's very difficult. That sort of in the white box setting, we now have kind of a good understanding of what the sort of worst case attacker looks like. But in sort of more restrictive settings, I think that's really the tough part, is sort of to come up with a slightly restricted adversarial setting where we can still nicely reason about sort of what a worst case adversary looks like. Regarding the assumptions about defenses, I think that's definitely something important, and that at least when we attack defenses, we also try to be very careful about that. If the defense sort of makes some assumption, or sort of claims it only works if some assumption is met, you better sort of make sure that your attack kind of respects these assumptions. And so I think one thing you mentioned is which is definitely something that's kind of a limitation of our binarization test, is like, imagine you had a defense where the robustness is somehow or like there's really something specific about the last layer of this defense that is like very, very important for the evaluation or something. Then of course, if we now go and say, oh, we changed the last layer, your evaluation doesn't work anymore, that might sort of be expected. I don't know of a defense that does this. And so this is kind of the reason we designed the test this way. In the paper, we actually discuss sort of different variants of the test. So for example, if your defense uses a detector, you kind of have to change the test slightly so that you're still actually using the detector for the broken model as well. Then there's some defenses that instead of having a linear layer as the last layer of their model, they have something like a nearest neighbor classifier. There also, we sort of have to adapt the test to sort of make sure that we preserve the structure of the original defense as much as possible, so that we can really make this argument in good faith that the evaluation really should be working in this case as well. That's a very good point, that the defense sort of doesn't apply. This test really can't apply in all cases, because sort of for any evaluation you come up with, it's probably going to be easy to come up with a defense where that specific evaluation fails.
Okay, yeah, thank you very much.
Okay, thank you. So the time is over. Before closing the meeting, I will give the floor to Hambra, who is going to present Isaac.
Hello, everybody. First of all, thanks a lot, Florian, for the great talk. And me and Florian have a little announce because we are co-chair of ISEC, which is a workshop co-located with CCS. And the deadline for the submission of the paper has been postponed to the 20th of July, so you still have time to submit your paper. I'll leave the stage to Maura, as we are short in time for the closure.
So thank you, Ambra, and also, of course, thanks to Florian for the super clear and nice presentation, and for answering all the questions from the audience. And now, I have a quick announcement. We will stop for a month with the seminar. Then we will be back for sure on September. So thank you all for joining, and see you next time.